So, hello everyone and welcome to J Classes by Sarkaz. My name is Arun Sharkar and I will teach you today. I will take you mathematics class. So, as we discussed in our previous videos, the JEE syllabus has 6 main divisions, namely algebra, calculus, trigonometry, coordinate geometry, vector and 3D geometry, statistics, probability, and mathematical reasoning. So, we are going to do algebra at first. And as I had mentioned earlier in my previous videos, that algebra has got 8 main chapters, and we did sets, relations, and functions. And today we are going to do complex numbers. So let's proceed. Okay. So what is a complex number? As we can understand from the definition given on the screen, it is a number which is written in the form of x plus iy, where x and y belongs to real numbers, and I is equal to root over minus 1. This is called a complex number. So what is, let's take up the main idea of a complex number. So what is actually a complex number? It is a mixture of a real number and imaginary number. So what is an imaginary number? Like, see, root over minus 1. Root over minus 1 is a number, like we can understand that suppose x is equal to root over minus 1. So x square equal, so if we square x, it will yield minus 1. So we have never heard that of this, that a real number or any type of number that we have known so far can have a square equal to a negative number. We know that always the square numbers are always said to be positive. However, in this case, we are able to notice that we are getting a square which is negative. How can this be possible? This can be only possible when the number is imaginary. That is, the number doesn't exist in reality, but we are imagining it. And since we imagine it, we are calling it an imaginary number. And a number which contains both a real part and an imaginary part is known as a complex number. Okay, so now we can see a complex number out here, which is written as z. Z is the complex number equal to x plus iy. So this x and y both are real numbers, and this I is the imaginary part or the imaginary number which can help a real number to become an imaginary number. So what is I? I is root over minus 1, as we can understand from here, and it is given that x is known as the real part of z and y is known as the imaginary part of z. Now let us see what is, if we want to say what is the real part of z or rez, that is x. But if we consider the imaginary part, it is iy. But if we take in consideration only, but as we know that I is a constant. Okay, I is a constant, but imaginary z and real z, these can be variable. Like these are different for different complex numbers. Hence, while explaining real part of a complex number and imaginary part of a complex number, we only take the real numbers, that is x and y, as we can see in this case. Okay, so now let's move on. Now we have to understand what is a purely real number and a purely imaginary number. Well, a purely real number has been taught to us since our childhood. Now, a number which has got no imaginary part, that is known as a purely real number. Now, how can we convert a complex number into a purely real number? In order to convert some number into a purely real number, it should not have its imaginary part. That is, which we learned in learned previously. That is IMZ, or the imaginary part of z. That it should be equal to 0. That is, y should be equal to 0. Why? Because I is a constant. It can never, I is a constant, that is root over minus 1. It can never be any other number. So what is the variable? That is, it is y. Hence y should be 0. Then z, the complex number z, is known as a purely real number. Z can be also known as, can also become a purely imaginary number if and only if the real part of z, or x, the variable x, it becomes 0. Then z becomes a purely imaginary number. From this, we can understand that real numbers, or what we call purely real numbers and purely imaginary numbers, are a subset of the complex numbers. Hence, if we consider a universal set or some set which contains all the numbers which we have learnt till date, is the complex number set. Okay. Now let's come to I. What is I? Or I is also known as iota. This I is the constant which makes a particular number imaginary. If we multiply I with any real number, it can convert that into an imaginary number. I is a constant which is equal to root over minus 1. Okay. Now if we square I, it will become -1. If we cube, if we raise I to the power of 3, it will yield -1 or minus of root over -1. And when we raise I to the power 4, it will yield 1. Okay. Now let us move on. Let us move to some basic integral powers of I, which is like as we can see here. Now we all know that if I is raised to the power 4n, it will yield 1. If raised to the power 4n plus 1, now let's see, 4n plus 1, what does it mean? I of I raised to the power 4n into I raised to the power 1. And what is I raised to the power 4n? 1, which we have done before. Hence, I into 1, it always yields 1. Similarly, in the other cases, as we can understand. Now, let's move to the other part. What is it given? I to the power n plus I to the power n minus n plus 1 plus I to the power n plus 2 plus I to the power n plus 3 is always 0. Now, let's analyze this. Let's consider I to the power n to be some variable. Suppose a. Okay. So, what can we see? A plus a into I plus a into I square plus a into I cube. So as we learned that I square is equal to -1. Okay. So a into I square, it becomes actually minus a, and we have and we have already got a out here. So a minus a, it yields 0. So it's cancelled. So now what we have got left? A into I plus a into I cube. Now what is I cube? As we have learned earlier, I cube is equal to minus I. Hence, a into I cube is nothing other than minus IA. So that also cancels, and hence the resultant is 0. And hence we can prove this result. So let's move on to the next part. Now it comes to representation of a complex number. So complex number can be represented in a plane which is known as the Argand plane or the Gaussian plane, or simply a complex plane. Now we represent a complex number as a point. So in this case it is P. Okay, so if the complex number is x plus iy, then the coordinates of P are x comma y. Here the x is the real axis. Why? Because the values on x always yield a real number, and y is imaginary axis. Y axis is imaginary axis. Since the numbers of y, numbers on y, it always yields an imaginary number when multiplied by I. That is, it represents the y axis represents the imaginary part of a complex number, and the x axis represents the real part of the complex number. Okay. Now these are now the real axis and imaginary axis. I hope everything is clear about this, and I hope you don't have any problem with this. So let's move on to the next part. Now here are some results based on the algebra and equality of complex numbers. You can just note it down, and there's no need to memorize this, as this is quite it's quite basic, and you can understand this quite well. Which is mostly important, that is the note. Complex numbers do not possess any inequality. Example, 3 plus 2y is greater than 1 plus 2y. It does not make any sense, because as we understood from the representation of the complex number on an Argand plane, it is well understood that the complex numbers are actually vectors. They are actually represented in the form of vectors. Hence, what can come into hence the complex number itself can never come into comparison, since it is nothing other than a point on a plane. Okay, the only thing which can come into comparison, that is the magnitude of a complex number, which we are going to discuss later on. So let's move. And here we come to this, as I mentioned earlier, conjugate and modulus of a complex number. So first let's discuss the conjugate of a complex number. So what is a conjugate of a complex number? If there is a complex number z equal to x plus iy, then the conjugate of the complex number z is said to be z bar, which I have written here. You can understand that quite well. And it is formed by replacing the I of the real part of the imaginary part of z. The I is replaced by minus I. That is, the conjugate of z is x minus iy. So now, if we think of it graphically, then how can we represent the conjugate of a particular complex number? So let's go to the picture we have shown you earlier. So here we can see that P is a point x comma y, which represents the complex number z. Okay, so my question is, if we want to mention the conjugate of complex number z, or we want to plot the conjugate of the complex number z on R1 plane, where is it going to lie? See, the conjugate is x comma y is x minus iy. Now I can be never I is always a constant. Hence, if we consider the real part and the imaginary part of the conjugate of z, it will be x and minus y respectively. Hence, if we want to plot this point on the Argand's plane, then it will come, then we can understand it is present in the fourth quadrant. And hence, what do we understand? That the conjugate of a complex number is nothing other than its reflection in the real axis. Okay, now let's see what is the modulus of a complex number. As I told you earlier, that a complex number is nothing other than a vector on the Argand's plane. Okay, and now what we have, and the modulus or the magnitude of the complex number is similar to the modulus of magnitude of a vector. What is it? The distance of that point of the complex number from the origin in the Argand's plane, the smallest distance, is known as the magnitude or modulus of that point of that point or the complex number. So how do we represent it? We put a mod sign over z, and its numerical value is equal to root over x square plus y square. Now how can we get this value? It is simple distance formula. The points of the origin, the coordinates of the origin are 0, 0, and the coordinates of the this complex number is x, y. Hence, what do we get by placing it in the distance formula? X minus 0 whole square plus y minus 0 whole square whole root over. So from that it comes to root over x square plus y square. Understood? Okay, let's move to the next part. Well, as we can understand, these are some results on conjugate and modulus of a complex number, and you can understand this. You all can evaluate this, and if you have any problems about these results or any problems proving them or understanding them, you can ask me in the comment section. Okay, let's move to the next part. Okay, now what is an argument or amplitude of a complex number? So as we can understand from the given image, that this a, or we can call it alpha, is the argument or amplitude of the complex number z, which is represented as x, y in the Argand's plane. So what is this amplitude or argument? This argument of a complex number is the angle formed by the vector OP, in this case OP, with the real axis. And its value is equal to tan inverse of imaginary part of x by real part of x. Okay, here are some important points about the amplitude or argument of the complex numbers. That its principal value. Okay, its principal value lies between minus pi to plus pi. Okay, now the actual value of this vector OP, it can lie in any one of the quadrants, be it the first, second, third, or fourth. Okay, however, the value of A has to be, the value of A can be any value. However, its principal value is what which lies between minus pi to plus pi. So how will we get it? As we can see in the next point, that we can get the principal value of the argument of z by a or pi minus a or minus pi plus a or minus a, accordingly as z lies in the first, second, third, or fourth quadrants respectively, where a is tan inverse of mod y by x. So what does this mean? If the complex number z lies in the first quadrant, then the principal value of the argument is as it is, we get it, that is a, simple. If it lies in the second quadrant, then we have to carry out pi minus a operation in order to get the principal value of the argument of z. Similarly, in case of the third quadrant, we have to do minus pi plus a or deduct pi from A in order to get the principal value of the argument of Z. And in the case of the fourth quadrant, since it is just in case of the fourth quadrant, in the fourth quadrant, the complex number, the argument we get is simply, we have to simply negate it, that is minus of A, and we'll get the principal value of the argument of Z. Okay, so, and we can also, and the last point states that the argument of Z is not unique. General value of the argument of Z is 2n pi plus A. So now what does this state? What is this general value? General value of argument of Z is the actual value of the argument, not the principal value. The principal value we can attain as we have learned it in the previous point. However, the general value, the actual value, can be attained by 2n pi plus A, where n is nothing other than an integer, and it varies from one case to another. However, we can also understand the argument of Z is not unique, since many complex numbers can have the same argument also. Okay, so now let's move. Here are some results on the argument of a complex number, and I don't think you would have any problem understanding these. If you have any, you can ask in the comment section below. Just note them down and try to evaluate them and understand them carefully. Okay, so now let's move on. Okay, different forms of complex number. Well, a complex number can be represented in the Argand's plane also, but it can be also represented in polar trigonometric form and the Euler's form. So what is the polar and trigonometric form? See, as we have seen, in case of this is also an application of the argument of the complex number. That is, if Z is equal to x plus iy, then Z can be also represented as r into cos alpha plus I into sine alpha. So this alpha is the argument of Z, as we can understand it very well, and this r is the modulus of Z. Okay, so this is how we can write the polar trigonometric form of Z. However, the general value of the argument, if we use the general value of the argument of Z, this alpha is actually the principal value, and hence it can be very misleading. So we can understand that hence we can't differentiate between different complex numbers with this form. Hence we have to use general value of argument of A, from using which we can get the right plotting of that complex number Z. And it can be done in the following method, that is r into cos of 2n pi plus A plus I into sine of 2n pi plus A, where n is an integer and the value of A varies as it moves on the first, second, third and fourth quadrant. Okay, so what is the Euler's form? As we can understand from the Euler's form, we can represent it as r into e to the power I alpha. Here r is, as we have learned earlier, the modulus of Z. Alpha is the argument of Z, and e to the power I alpha, it represents cos of alpha plus I of sine alpha. Okay, so now let's move. Now here comes the concept of rotation. Now what is this concept of rotation? Well, in the concept of rotation, you have to consider at first two complex numbers Z1 and Z2. What we are doing, we are rotating Z2 with respect to Z1 at an angle alpha. If we do this, it will lead to the formation of a new complex number which we can call Z3, and which we can represent in the following figure as in the form of a triangle. Now if we actually see, it forms a null vector, and the angle alpha here is the angle of rotation, keeping Z as the point of rotation, Z2 as the beginning point and Z3 as the ending point. Okay, now we have to find this value of alpha. So what is this alpha equal to? Alpha is the argument of Z3 minus Z1 by Z2 minus Z1. Why? Because as we can understand, alpha is the argument between the Z2 Z1 vector and Z3 Z1 vector. How we can get that vector? First we have to get the Z2 Z1 vector, that is Z2 minus Z1, and Z3 Z1 is Z3 minus Z1. Now why are we doing Z3 minus Z1 by Z2 minus Z1? Well, I feel you remember what we did in results on arguments. Here what we see, here it is, that argument z1 by z2 is equal to argument of z1 minus argument of z2. Okay. Now if we consider this alpha is nothing but the difference between the argument of the vector z3 z1 and the vector z2 z1. Hence we do this, and from this we can find alpha in this way. That is the argument of z3 minus z1 by z2 minus z1. And the z3 minus z1 by z2 minus z1 is equal to the modulus of this into e to the power I alpha, where alpha we have said is the angle of the rotation. Okay, understood? Now we have to consider a note which says that we have to always mark the direction of the arrow in anti-clockwise sense. Why? As we have learned earlier, that the anti-clockwise direction is taken to be the positive direction. Hence, we have to always take the angle of reflection in the anti-clockwise order. Okay. Now let's move to the next part. De Moivre's theorem. Well, De Moivre's theorem is one of the most important theorems in complex numbers. So, what does it state? If any integer n, if we take an integer n, then cos theta plus I sin theta whole to the power n is equal to cos n theta plus I sin n theta. This theta is the principal value of that complex number. If we take the general value, we know how to notate. We know the notation 2n pi plus theta, which we have learned earlier. Okay. So now let's see another part. If n is any rational number, then one of the values of this is cos of n theta plus I sin theta. I sin n theta. Understood? Rational number. For integer there is only one value, but for rational numbers there can be many values. Okay. If n is any, now let's move to the other part. If n is any positive integer, then cos theta plus I sin theta whole to the power 1 by n is equal to cos of 2k pi plus theta by n plus I of sin 2k pi plus theta by n. Here we can understand that we have to take the general value and not the principal value. Okay, and the values of k is given below. So I feel you have understood De Moivre's theorem, and if you have any problems regarding to that, you can ask in the comment section below. So now let's move on to the next part, which is the nth root of unity. So what do we mean by the nth root of unity? By nth root of unity, we mean any complex number z, any complex number alpha, which satisfy the equation z to the power n is equal to 1. Okay, so now if we take z to be a variable complex number, z to the power n equal to 1, it can have n values or n roots. These n roots are known as the roots of unity for the complex number z. Now we can see some results regarding the nth root of unity of a complex number. The first result says that if the roots of unity are 1, alpha square, alpha to the power n minus 1, that is, it is a GP going on, as you can understand, then alpha is equal to e into e to the power I 2 pi by n. Okay, understood? Now let's move on to the next part, which says 1 plus alpha square plus alpha cube plus dot plus alpha to the power n plus n minus 1 is equal to 0. Now how can we understand this? Simply we should apply the sum of GP, from which we can get alpha to the power, from which we get this sum to be equal to 1 minus alpha to the power n by 1 minus alpha. Now alpha to the power n or z to the power n is equal to 1. Hence the numerator becomes equal to 0, as the entire sum is equal to 0. Understood? Okay, let's move to the next part. What does it say? That if we multiply all the nth roots of unity, then we'll get minus 1 whole to the power n minus 1. Now how can we get this? If we multiply all the roots of unity, then we can understand that it is an AP, sum of a, then it will come to alpha whole to the power 0 plus 1 plus 2 plus n to the power minus 1. N minus 1. Hence, what can we understand? This is the sum of an AP, and from that we can understand that we get minus 1 whole to the power n minus 1. Okay, if you have any problem in evaluating this, you can ask in the comment section below. I will later answer this. Okay, so let's move to cube root of unity. Now, until this point, we have known that suppose there is an equation x is a variable, x cube is equal to 1. So what, until we knew, until we knew complex numbers, what did we say? That if x cube is equal to 1, then x is also equal to 1. Why? If we solve it, then x cube is equal to 1 can be said x cube minus 1 equal to 0, and we can factorize it as x minus 1 into x square plus x plus 1 equal to 0. Now since we know that x is now in the previous, before knowing complex numbers, we knew that x is a real number. Hence, if we solved x square plus x plus 1 equal to 0, it comes as the sum of two squares equal to 0, which can be only possible if it became 0. Now it's not possible. Hence, we always took x equal to 1. Okay, so with respect to the x minus 1 part. However, it can have different values too. Now, since we know complex numbers, hence we can understand that from the part x square plus x plus 1, we can also get. Now we know that we can also get complex numbers as the values, as we know that imaginary numbers are also roots of a certain equation. Hence, if we solve that part x square plus x plus 1 equal to 0 using Sridhar Acharya method, then we will get two values, minus 1 plus root 3 into I by 2 and minus 1 minus root 3 into I by 2. These values are known as the cube roots, are known as the imaginary cube or the complex cube roots of unity, and they are denoted as omega and omega square. Now, why do we write it as omega and omega square? If we square any one of these, then we will get the other value. Okay, so what are the cube roots of unity from now? 1, omega and omega square. Okay, understood? Let's move to some of the properties of the cube roots of unity. If we add all these cube roots, it will yield to 0. Why? Because we all know the cube root, that the sum of all the nth roots of unity is equal to always 0, which we learned here previously. Okay. Now we also know. Now let's see. Omega cube is equal to 1. How? What is actually omega cube? It is 1 into omega square. Hence, it is the sum of the roots of the equation x cube minus 1. Now, if we apply our knowledge of quadratic equations, we can get that for a cubic equation, the product of the roots is equal to the value of d, or the constant term, is equal to the constant term into minus 1 whole to the power 3 minus 1, that is 2, and minus 1 whole square. Hence, the product of the roots is simply the constant term. And here the constant term is nothing other than 1. Hence, the product of the cube roots of unity is nothing other than 1, or the omega cube is equal to 1. Okay. Now, here is another part. 1 plus omega to the power n plus omega square n is equal to 0 if n is not equal to 3m, and 3 if n is equal to 3m. I'm leaving this as an exercise for you, and if you can't evaluate this, you can ask me in the comment section below. Okay. So here are some applications of the complex numbers in geometry, and these are what we have learned till so far in coordinate geometry and Euclidean geometry. You can apply this easy. You can understand this easily. If you have any problems regarding to this, you can ask in the comment section below. And our class ends here for complex numbers. Later, I'll have a problem solving session regarding to complex numbers and set relations and functions. So goodbye for today. And I'm saying you all again, that if you have any problem, please ask it in the comment section below. Thank you.